Very good afternoon, all. Welcome to the class. Resuming on heap sort. We have already started talking last time, and we said that there were two steps. And first step we have discussed in more detail. And effectively, if you remember the kind of a initial data structure or initial array which was stored into the list had some data like this, and we assumed and discussed their swapping and interchanging of the values wherever needed about all different logics. So this is what we initially assumed, that this is what is our initial array. Effectively, what we said was, let's review our step one, which we have discussed, that if I have this data on various indexes starting from 1 onwards. So if this is index 1, this is index 2, and so and so. So effectively, I could say for any index I, this is to be considered as in equivalently as a complete binary tree. And once we have this corresponding to any node index, its left child will be always at 2i. That is what we discussed. And right child will be always at 2i plus 1 if child exists at all. If they don't exist, obviously not. And the parent, if parent exists, this was always going to be I by 2 with the floor of this. And using this property, we said that we are going to convert it into a max heap. Every child or every node of this CBT will be converted ultimately into a max heap where root should be greater than equal to its children. So both children, if any. So that will be the property. And by this process, in step one, effectively what we discussed was that we said that non-leaf nodes will be converted into max heaps, and leaf nodes are already satisfying. So non-leaf nodes were present from n by 2 down up to 1, and we call for each of them an adjust function. For adjust, we needed 3 parameters: array, the corresponding index or I, whichever I am passing, and the I was which I was passing from here, let's say, and n total number of values, so that I could see this is going out of limit or whether child exists or not. And we discussed that heapify is another word used in some books like in Corman, etc. For the word adjust. It is one and the same thing. So step one we have discussed. So we said that my heap sort primarily had effectively a step to be discussed in two ways, where step one, we went for I equal to n by 2 and so up to 1 we went, and we called adjust. And then based on adjust, we were able to adjust the corresponding node to become heap at that point downwards. So we started from the reverse leaf order, non-leaf orders, and then we did this. Once we come out this, the total array is, or total array or total CBT is now max heap. And once it is max heap, what we discussed was effectively my root will get the highest value. Others will have something available, but this is going to be highest for sure. Now, if I say that, let's say we have got some data, so effectively root being highest means in the array, I have got here 77 at index 1, and from index 2 onwards, all other nodes are satisfying the heap property, and at the last node, we have got some data. Let's assume at the last node, we have got value 5. And in between these, all nodes are satisfying the max heap property, and this is currently available. Now, let's talk of a step 2 and do that. So how my adjust function was used? Adjust function, let's say I started from some node for this, probably let's say that will mean I will try to compare with both sides and find 61 is higher. So 5 will reach here, swapping will happen. 5 will be compared with its only one child. 5 will ultimately go here. 99 will ultimately come here. And This was the process which we have used earlier. So similarly, this side, it could have first comes 26, then 26 could have gone down, 59 could have gone. So effectively, this means we had something like this into my max heap now. So step 2 now comes. I say my root position is highest, root's value is highest. Hence, it can go to its correct position. If I want ascending order sorting, so this has to be the last value, its correct position. This position is guaranteed to be the last element into the sorted array. So what I will do, I will say, let 77 go to the last, meaning that 77 will reach here and 5 will come. So effectively, correct position means last position, nth position. Because my array list is 1 to n, not 0 to n minus 1. So nth position is the last. So I will bring 5 here and 77 here. Now I say root coming here effectively meaning that 77 has reached its correct position. So treat your list to be of one lesser size. This list will be now, this will be the new array which I want to sort. So assume that you have decreased from n, as earlier it was 10. Now let it becoming as 9. 9 will mean I will consider my list as 5, 61, 90, 59, and so up to the second last position, whatever. So effectively, what it means is in this, if I see equivalently logically, what I did was 5 I brought top, 77 I brought down. This is correct position. Remove this, forget about this, and now you have again the function for adjust to be called because root has disturbed. So effectively now it means I have 5, 61, 59, and so. But now total nodes being 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is index 9. This is index 1. So I say 10th node I don't consider. This 10th node, whichever was, I'm not considering at all. Now, only root is not satisfying the max heap property. All other nodes are already satisfying. That is, we can guaranteedly say. And if it is so, the adjust function is always able to adjust from a particular node to downward children with a single call. So I will mean now adjust over root should be tried, and it will again mean the highest value coming on the root. And once I have done that, then I can repeat the process. So what I require is effectively now simple logic that I want step 2, which I said is after step 1, effectively I need is swap your array 1 with array last. With the last means effectively array n. Once I have swapped this, what will be the next step? Assume that last element doesn't exist because it has reached to correct position. So I will say treat n to be minus minus. Reduce the size. Effectively means n equal to n minus 1. Whether you can take a separate variable or reduce n because you are using function. So n will be called by value passed. Even if you decrease here, once you come out of the function, n will be actually restored to its correct value. So you can safely play with n also to be minus minus. Now what? Effectively, you have your new list with array 1 to n minus 1 or new n. You have to adjust that. Adjust call to be done. And for adjust call, array is passed, and we are supposed to pass the root of the tree which is to be adjusted where root doesn't satisfy, but its children are satisfying the max heap property, then array adjust function or heapify function works easily. So whether you call it a heapify or adjust, you need to call it for a particular index. And now the index will be the node which has got disturbance. So the node which has been disturbance is root, you are right, and the n has changed. So new changed n will be passed, and this process to be repeated. Repeat for long. How much time? How much time you should repeat? Obviously, as long as the sorting is not complete. That means sometimes up to while. For how long I should do this? I can probably think that as long as list has more than one element, the swapping and heapify, etc. is needed. So if n is greater than 1, obviously it has more than one element, this process will work. And when n becomes 1, then obviously we can stop. So this way I can repeat the step 2. So my heap sort function can be now implemented. Whatever parameters you have used, for that you will write your step 1, the coding which you will do using for loop for I equal to n by 2 down to 1, etc., etc., adjust function being used. And then this is step over. So then you have a step 2, the code which we have written while n greater than 1. And then obviously now I will be having my swap function or swapping of the value, n to be decreased, adjust to be called again and again with 1 as parameter. And this process to be repeated, and ultimately the sorting is done. Now, why we are talking all this is now you can easily see heap sort will be able to do all sorting using a concept of a CBT, but advantage being that in worst case also, or average case also, or of course best case also, in terms of a time complexity, this performance is order of n log n. In fact, at this point now we can easily say that if you talk of a quick sort, or if you talk of any other sorting like insertion sort or selection sort or bubble sort, all these in worst case, their performance is not good. Worst case, their time complexity is order of n square. You will analyze all this when you study design and analysis of algorithm next semester. But now we have easily seen that you could easily do, except for recursive functions like quicksort, you can easily identify the total steps for insertion and selection sort. In worst case, they will become order of n square. Merge sort is the only algorithm which works in worst case also the order of n log n. So worst case also it is good, and it has complexity of n log base 2n. But the merge sort has a disadvantage, and that disadvantage was that it requires extra space complexity. So that was the problem with the merge sort. Hence, now heap sort becomes one of the fantastic algorithm which does not require extra space because we are not creating any extra array. CBT is logically discussed only. Everything is being done on the same input array itself. And worst case time complexity is also order of n log n. Of course, it might not be as good as your merge sort because this log base is not 2 always in the best worst case, etc. But still, this is much better than n square. So compared to other algorithms, heap sort has reasonable advantages. Hence, it is studied and preferred. So with this, I think I will leave now. You should be able to implement your heap sort. So implement heap sort, that I'll give you the homework. And for implementing heap sort, you should be using the adjust or heapify function also. And that coding also we have used already. So this function can be used iteratively, and it can also be done recursively, because once you have adjusted for one particular index, it has gone to some child side max index. From max index onwards, recursive call can directly be used. So wherever max index has reached, from it downwards, if you have to redo the whole adjustment, effectively the same recursive call to the same adjust function can be done. Hence, you can try those. So I will say try to implement adjust or heapify using iteration, and also try to implement using recursion. Good students should be able to think that easily. This we have already done in some detail. Having said that, I will effectively say now sorting is clear. We have some time left for today's discussion. So I will resume back to my binary search tree considerations, and we will talk of the deletion situations. Deletion, how to do, we have already in the last lecture of the BST, I have also given you some hints, but before we resume there, let me go and show you the binary search tree insertion code so that you recall that, and then we will be talking of the deletion cases also. So I asked you to implement binary search tree. This can be the structure declared, obviously, and based on this structure, now you have got the function to be made. So from main, I can easily start. I take BST initially as a null because that is the way we work with the BST. And in BST, creation will mean effectively insertion of the value one by one into initially empty BST. And then once it has anything as a root, everything to be stored only at the leaf level. If it is to be stored at the leaf level, there will be exactly one place and we will be doing the insertion logic. So if I have an insertion to be called, I will say BST insert BST, and because it will be returning always in root pointer, so it will be assigned to BST. I want to search value. I'm going to search, and then I'll say item print or with in order traversal if I want. So first of all, let's see insertion code. So I say if initially a new node is being created, data is being stored, it's left pointer null, right pointer null, because this is always going to become a leaf. If it is always going to become a leaf, I can safely do all this work. Now, if initially BST was null, the PTR itself will become the root, hence that will be returned. Otherwise, I will say take a current pointer. I will always maintain the previous pointer and I will reach to the null position going downward to the children and direction. If value is less than current root, that is root data, I will go to the left side. Otherwise, I will go to right side. Keep on repeating. And once we are out, then the value will decide, because on the previous left or right side, this node is to be connected. So previous left or right, how to decide? If val is less than my previous data, it means it is on the left side. Otherwise, it is on the right side. This connection established, and then overall BST, whichever pointer was, that BST pointer will be returned. Even if it is unchanged, the same unchanged will be returned. Search function, very similar. I will say till I don't reach to the null. If the data found, effectively over, and return or break, whatever you say. If val is less, I need to go to the left side. Otherwise, I need to go to the right side. Keep on repeating. Either I'll get the value or I will be able to stop because I reach to null. And if null is reached, I will return null. Otherwise, the node which has been found, that will be returned. In order, standard simple function, standard 3 lines, 4 lines code, and I can easily see that via in order traversal, the sorted list will be displayed for the corresponding BST. So this is the sample implementation. Of course, many of you, I'm sure, must have already done that. So now going back and let's resume the deletion discussions related to this. So now I'll say that we have understood the insertion and the searching logic for the BST. Let's talk of the deletion cases. So let's assume I have something like this. This side I have less than 30 will mean obviously this. Maybe this side I have something greater than 30. This side could be even lesser. This side could be something in between. This side could be, let's say, 5. This side could be, let's say, 3. This side could be 2. This side, I say 60 has some data. Let's say 25 has another data on the left side, which is 22. 60 has something, let's say 50 here. 60 has something greater, let's say 670. 70 could have something lesser, let's say 65. So I have a BST like this. Now, let's say here, think of a deletion cases. If I am asked to delete, let's say 2 or 22 or 50 or 65, I find deletion is easy. Effectively, this is a leaf node deletion. So if you think of deleting this, effectively, you have to just make this as null, no other node gets disturbed. 22 to be deleted, make this as null, no other issue, no other node getting disturbed. Delete 50, just you have to do this change. Delete 65, you have to do this change. That's it, easy. No other node gets disturbed. Hence, things are easy. But think of a different situation. Let me carry this page to the next slide, and then I will be able to discuss what we want to see. So if I say I have got this thing to be shown and I want the deletion to be applied over this particular one, let me just adjust this so that it doesn't. Yeah, okay. So I have this BST along with this, the deletion to be discussed. So I say now the deletion has a different kind of a situation. First, obviously, I said case 1. So deletion I will take in multiple cases. Case 1, leaf node to be deleted. Effectively will mean things are easy. For example, if I say delete 22. Delete 22 will mean effectively search for 22 and store its parent into previous. Because via previous the link will be established. So effectively this will mean previous will be stored at 60 and now 60 is my previous node. And I say 60, sorry, I was talking of delete 22. So I will say that will mean 22 the previous node is at 25. So effectively I will reach to 25 node. This will be my previous node. 22 is on its left side. Effectively this link I will make as a null and free or return whatever node for the 22 I wanted to do. So effectively deletion for all leaf nodes is easy, no changes, no disturbance. But now other situations. Case 2. Think of a deleting, let's say value 3 or value 5 or maybe 25 or maybe 70. Think of this deletion. I'm talking of this value or this value or even could be maybe 10 also. I can say 10 also or 25 or could be, let's say, 70. All these nodes are effectively a single child node. Single child node means they don't have both children. So effectively deletion will be still easy. What I can do is do like this. For example, if I'm at some node 5, I have here 3, I have here 2, I want to delete this node. I say no other node will get disturbed if I just link like this. All properties will remain same and no disturbance. All nodes will still be okay and all BST properties be okay. Just simply you have to bypass that node and accordingly your relinking will be possible because no other node is getting disturbed. So this way I can do. Same is the case for the 5 also, same is the case for the 25, 70, 10. Even if I say I am at node 20, this side is at 25 and this side is at 22, I say 25 deletion will mean 20 is right side because this was right child. So now you can bypass this. This is to be deleted. Then deletion is still simple. You can simply have this 20 is right child now to become this 22, and then you can free or do whatever you want to do. And 20 effectively connecting like this getting deleted, no other property gets violated. Everything still works well. So this can be one of the easier ways to solve this problem. Let's see now. What I mean is that case 2 deletion, single child deletion will again mean search for this value, search for that node, and store previous, which is its parent, etc. And then I will say previous left or right side, whatever I had this node, that will actually point to the node being deleted. Delete nodes only child, left or right child. Only one child exists, and the same node will be done. So whatever that node's left or right child was, now my parents left or right, whichever applicable, whichever side, whichever was the side for delete node. The same side I will use, and I will have this linking done. So delete node can be done, and I can easily do. Still easy, and without any further looping, etc. After searching, the process will be easy. After searching, few lines only needed. So effectively, it can be done in order of one time. Leaf node also, if leaf node was being deleted, that case also, that is case 1. That case is also effectively after searching, it will be order of 1. But then case 3 is going to be much more complex. Node having both children. Now that becomes a challenge. And that is the most difficult problem to be handled in the deletion. What does that mean? For example, I say in this tree, I say delete 20. Or maybe 30, or maybe 60. Any node like this. This one, or this one. Because they have both children. Just imagine, delete 20. Now you can't delete it easily. For example, if I say I have here 30, you have here 20, you have here 10, you have here 5, you have here 25, 25 has something here 22, and could be anything downwards up to anything. This to be deleted. Now, deletion cannot make the linking 10, 30 with the 10 or 25, or there is a lot of complexity. Either you have to do some readjustment into all nodes, many nodes to be readjusted, and things become really complex. And you can't effectively bypass 20 because 20 has both side children. You can't simply have this side linked. If you link this side, what will happen to 25? If you try to think of something, so some other node will get disturbed. If links you are able to maintain, then your property, BST properties should not get violated at all. So those values, properties must always remain true. So you have to ensure everything. Hence, case 3 becomes difficult. So effectively for case 3, the solution is that if I am trying to delete a node having both children, I will effectively not physically delete this particular link, etc., and don't disturb the structure. I will say replace the value at this node with successor value, and successor means effectively in order next value. What I mean, 20 to be replaced with a value which will be next in the in order traversal. Why I am claiming? For example, in this case, 20's next value, let's say if I have something like this, let me take another page and explain there more clearly. So if I say you have 30, I'm talking of a 20 to be deleted. Corresponding to 20, I have lot of connections downwards also. I have lots of connections like this also. Like this also could be there. Maybe I have here, let's say this value is a 24. This side is, let's say, 22. And this could be, let's say, 23. I have a structure like this. Now I say delete 20 is actually disturbing too much things. I will say replace it with its successor and remove that success. And delete the successor. Replace with value of successor and delete successor node. Means what? I say 20's successor is 22. In the sorted list of this traversal, 22 will come here. So I say, if I replace this value with 22, BST properties all still okay. That is the advantage. Because whatever values were less than 20 are still less than 22. This side values are greater than 20. I have brought the next value only. So except 22, no other node is having a problem because just next highest with the 20 is 22. All other values are guaranteedly greater than 22 because after 20, 22 was getting printed. So all other values are greater than 22 and they will be still on the right side of 22, hence still okay. So the only thing is now I will say replace this and try to delete this node. So my deletion will shift to some other node. But I say this is going to be easier because my successor is guaranteedly going to be either a leaf node or a single child node. It is never going to be a both children node. And in this case, it means this will become a case 1 or case 2, and both cases are easy to program. So effectively, my case 3 solution will be find your successor node, and your current node's data will change, which will become your successor node's data. And then you will effectively say delete the successor node. So this is your successor node, and this deletion will be using either case 1 or case 2 as per possibility. Hence, the repetition will never happen and case 3 gets solved like this. So how to find successor? You have to think of a logic. Effectively, successor node for a particular value will always exist at a specific location. I will say you have to go to right child, and from right child, then you have to go to leftmost child of this. So right child, you have to go to the right child of the current node because successor is available only on the right side. But from the right side, the leftmost child downwards keep on going down. Wherever the leftmost child is finally present, which has no further left, that will be the successor. For example, 20s, I went to the right side. 25 successor is go down, left, wherever you reach. For example, I say 25 is the successor, go to the right side, and this is going to be, because there is no leftmost, left. 30 is the rightmost child or 30 is successor. Let's say I have some structure like this. I want a 30 is a successor to be found. So I will go to 30 is the right child. 30 is right child means this. Go to its left child. It might have further left child, might be whatever value is available here. Let's say 40, then the 40 will be the successor over 30. So this process will be effectively followed to have all this implementation. So with this, I will stop and I will give you a practice problem for good students at least. Think of doing the deletion implementation. Implement deletion also. And what I will say, for deletion, you will write your node or whatever delete function, whatever return type. In this, based on certain if, either you can have a delete one function or delete one body code written. Else, based on some condition, you can have delete two body or delete two function. Else, it will be correspondingly delete 3 case. For case 3, find your successor and then apply delete one code or delete two code for successor node. Hence, this overall implementation can be done. So I will say good students must try this, and that will be a good practice for those students who really want to enjoy programming. This can be even made easier if you can store parent link into a node. In each node, if you store parent link, like for ancestors, I have asked you to implement that. We have already discussed. If you have stored this, deletion implementation will become easy. Then things will become much more easier. Previous pointer need not be stored, and this can become easy. So those who have already tried that part for ancestors implementation, if they try to use your parent link also, then things will become even simpler. Having said that, I think it's the right time to stop. And of course, if you can implement this, good. But because of the syllabi contents in the Horowitz and Sahni, deletion logic is only theoretically explained. Coding is not done. So coding you are going to do next semester also in algorithms part. But good students must practice now. And then you will have a lot of confidence in doing all this. Bye-bye. All the best to all of you. Implement heap sort using iterative at least. Good students should implement heap sort using recursive adjust function also. And good students should also try to implement a deletion on BST. Bye-bye. All the best to all of you.